Good afternoon, I'm John Yemberg with NASA's Office of Communications. Welcome to the Science, Research, and Technology briefing for the International Space Station. What we're going to be doing today is talking about some of the cargo launching to the International Space Station aboard SpaceX's 7th resupply mission. This launch is Sunday at 10:21 a.m. Eastern Time and will be broadcast live on NASA television. For those watching at home, and for those watching on NASA television and on the web, you can follow us and ask questions using the hashtag AskNASA. Without any further ado, let me introduce our panelists. Going from left to right is Julie Robinson. She is the Chief Program Scientist for the International Space Station. Michael Stinger, he is the Principal Investigator for Fluid Shifts at the Wiley Science, Technology, and Engineering Group. And Alessandro Grottoni, he is the Principal Investigator for Microchannel Diffusion at Houston Methodist Research Institute for CASIS. We're going to start with Julie, and then we're going to take your questions.
Well, thanks a lot. It's great to be here ahead of a SpaceX launch, our 7th SpaceX launch with cargo to the International Space Station, and tell you a little bit about the research that's going to be going on and the research that's supported by the flight. There are about 35 different experiments that are going up or down on SpaceX 7, and those support the over 250 active investigations we have going on ISS right now. That's about 700 kilograms of mass up and about 400 or more kilograms coming back down with samples and so forth. And of course, I'm not going to tell you about 300 investigations. I'm not going to tell you about 35 investigations either. But I did pick a few of my favorites just to give you a sense of the breadth and the different kinds of disciplines and the really innovative things that are going on the space station. We do have a new facility going up this flight. The facility is called Wet Lab. It is a piece of hardware that will let us do on-orbit gene expression, so we can understand from any sample from any kind of living organism what kinds of genes are being turned on and off. It's what we call on Earth a PCR machine, or polymerase chain reaction machine, and that's going to enable a lot of additional work in genetics and in understanding the mechanisms of the effect of spaceflight on organisms. In a completely different realm, another instrument going up is called Meteor, and this instrument was an instrument that had originally been manifested on the Orb 3 launch that failed and was damaged, and then we have a new replacement instrument going up on this flight. Meteor will be mounted in the space station, and it's a specially designed camera that is tuned to look at specific wavelengths of light so that it can tell us the chemical composition of different meteors as they re-enter the Earth's atmosphere. It can see signals from iron, calcium, magnesium, and sodium, and that will help astronomers to study those meteors and know what their composition is. On Earth, you can do the same thing, but you have the whole atmosphere getting in the way. So it's a great opportunity for scientists to have this on board the International Space Station. Another experiment that will be going on is Veggie 3. This is actually our second experiment, even though it's numbered 3, growing plants in a greenhouse that are really eventually intended for human consumption. Our first flight, we flew a special kind of red romaine lettuce, and we brought that home and tested it to see if there were bacteria there, or if it would be suitable for food. It did a pretty good job passing those tests, and now we're flying a kind of a cabbage called Tokyo Bacana cabbage, and we don't have all the paperwork in place yet, but we're quite hopeful that the crew will actually get to eat this cabbage after they grow it on ISS this time. Also, in studying the interaction between the crew and living organisms on the space station, we have an investigation called microbial tracking. This investigation is looking at the surfaces of Earth, such as this surface you see, which is the galley table surface where crew members eat. And just like in your home, those surfaces can become contaminated with different kinds of bacteria. What microbial tracking is looking at is all of the different ways that bacteria come to this closed environment, the way that they spread, sampling surfaces and air and sampling the crew, and understanding that environment over the course of a 1-year period. This helps us to design future studies that will have a closed environment be safe for the crew members. We also have experiments that are really more focused on either national lab, commercial objectives, benefits on Earth, or educational objectives, and not focused on space exploration. And so some examples of those, the Micro-9 investigation, which is also looking at microbes, will be looking at yeast. These are the simplest complex cell that you can study, and so scientists are looking at how do yeast communicate with one another when they're forming a colony. This is kind of a model for the way that stem cells might coordinate with each other as they start forming something like a tumor or some kind of a growth that we might want to manage. And so the scientists will be looking at the communication using ammonia between these cells and have different kinds of yeast that have different genes included and not included to help them get insight into these processes. And this is sponsored as a national laboratory investigation by CASIS. Another set of investigations that works closely with CASIS is the commercial partner NanoRacks. NanoRacks flies a variety of self-contained small experiments to the space station every flight. And this is a really special flight because there were a number of students who had investigations on the Orb 3 flight that were lost. And so they're getting to refly those investigations. There are dozens and dozens of these, but I picked a couple of my favorites to tell you about. And there'll be some students tomorrow at a briefing that'll be able to tell you in their own words about their investigations as well. One of these is an experiment looking at chlorella algae. These are the kind of algae that grow in a freshwater pond, and they're interested in seeing if the photosynthesis changes between the ground and being in space. So they'll let the algae grow and measure the amount of oxygen they produce. Another great investigation is called BE rad shielding. It's students that are flying basically a little Geiger counter, and they've got a piece of material that's a candidate for shielding for future space missions. So these young students have looked at high-density polyethylene, which is a plastic that you're probably familiar with, but this one is infused with boron. So they're looking at the ability of that shielding material to protect against radiation. And so they'll have the shielding material, it will be automatically moved in front of and away from the Geiger counter, and they'll be able to take measurements from that. And one thing that is great about it, especially the chlorella investigation, students started on that when they were in high school, and now they've gone on to work with college professors to do some of the programming themselves. So it's great to see students growing up and working on these investigations over their academic careers. So as I mentioned, we have exploration-focused research on the space station, and we have commercial national lab Earth benefits-focused research on the space station. And we'll have a number of scientists here to talk to you about their specific research in those areas. In the meantime, if you want to keep track of all 350 investigations and hear about the highlights going on, you can always follow me on Twitter at ISS_research. And I'd be happy to take questions about our research. Thanks.
Thanks. If you have a question, please raise your hand, wait for the microphone, and state your name and affiliation. And if you're with social media and you want to throw your Twitter handle in there, feel free to do that as well. Questions? Front. Go ahead.
Hi, Ken Kramer for Universe Today and the Northeast Astronomy Forum. For Julie, I wonder if you could review a little bit about the one-year crew. What have we learned so far? What are they focusing on? And the second question is about the food that came back. You said, what was the result that you found that would enable you to actually allow the astronauts to allow them to eat the new food, the cabbage that you are sending up now? Thanks.
Okay, so the one-year expedition is a really exciting thing going on. We're about 3 months into it so far. And in that expedition, we have an astronaut, Scott Kelly, and a cosmonaut, Mikhail Kornienko, that are both participating in a series of joint investigations that are collaborative between U.S. scientists and Russian scientists together. You're going to hear about one of those investigations on our panel today, so I won't scoop him. But let's say that we think the investigations are going incredibly well. I've been in a number of meetings with our Russian colleagues where we were previewing some of the early data that's come down even before publication. And what I'm really seeing is a huge influence on the way that we will be able to explore as a species in the future, as we get the different ideas that Americans have and the different experience that Russians have, and we get those together into common principles. So some of the areas we're working on are behavior and performance, sleep deficits, the ability to do complex tasks right after you land. We're also looking at the health of the crew on orbit, and in their exercise regimes and fluid shifting and so forth. And so it's a really exciting time to have this mission kicked off. To answer your second question, what we did with the romaine lettuce is we brought it home. We didn't let the crew eat it. And we brought it home and tested it for bacteria. The goal is to, because we know that microbes can be more virulent in orbit, or at least there have been some studies of some kinds of microbes that suggest that, we're concerned that there might be bugs growing more rapidly there than they would on a garden on Earth. And of course, in a garden on Earth, we're used to a few bacteria. You just wash your produce maybe in water, or maybe you use a little soap or something, and then you eat it, and that's fine. So we want to be sure that there's nothing growing on the lettuces and so forth that could cause harm and make the crew sick. So when we tested that, it looked really good. One thing about the veggie system is it uses these disposable plant pillows to grow them in, so that those can come in sanitized every time, so that you're not adding bacteria as you grow plants over and over inside the system. So I think we're getting close to that first bite of space lettuce.
Julie, do you foresee them using astronauts on the space station eating veggie experiments soon?
I do, and there's a couple of reasons for that. One is that when the crew members eat only preserved food, they do start having nutritional deficiencies over time. Not everything is well preserved in a pill form. Preserved food is better than just taking vitamin pills. We've had some studies that showed that. But in fact, as we all know from our Health on Earth, eating fresh leafy greens is a really important part of a balanced diet. And so if you think about exploration missions that are much longer than the 6 months we're typically doing on ISS, certainly a 1-year mission, it starts mattering more, and we bring fruit to our crew, fruits and vegetables up to the crew when we launch a flight many times. But someday when we're going to Mars, we won't have the ability to bring fresh fruits and vegetables to them. And so veggie provides an alternative so that the crew members can grow a little bit of their own vitamins, and that can really improve both their nutrition as well as a little bit of their mental health too.
Jim Siegel, I'm with the Celebration News and Spaceflight Insider. Dr. Robinson, I have a general question about, well, let me put it this way. My readers are interested in the benefits of these various experiments, not only to astronauts, but maybe more importantly to people here on Earth, what benefits they will have. Now, I was reading a little bit about the telomeres experiment having to do with chromosomes and the ends of the chromosomes. And I wondered if you could comment on whether you thought that experiment, first of all, that experiment has some benefit to people on Earth ultimately, and secondly, are there any other experiments that are on board that might have a particular benefit to Earthbound humans?
Yeah, so it's interesting you mentioned the telomere experiment. Back to basic biology, telomeres are on the ends of chromosomes, and they're important for having the chromosomes align properly when the cell divides. And it's been shown in some organisms and some cell lines that as the cell line ages, the telomeres get shorter and shorter. So this really has to do with accurate production of cells and aging. And if you start thinking about that, what does that kind of knowledge mean for the basics of how we understand illness? One of the things that we see as people age is their reproduction of their cells. Their cells have more and more errors in them. Mutations are more likely. So telomere length really links to aging. And the other thing, of course, that happens in space that doesn't happen on the ground is it is a less friendly radiation environment. It's not as bad on the space station as it would be in deep space, but those kind of factors are also a part of changes that we see to chromosomes on the space station. So these kinds of studies that are really trying to understand the mechanisms of cell division and how those relate to errors that happen in cell division, those are at the core of understanding aging and perhaps even improving our life and health back here on Earth. One of the things that is really exciting about the National Lab designation of the space station is that it really opens up half of the ISS to be used for these kinds of experiments, the kinds of experiments that might be focused on benefiting life on Earth, but not so much focused on future exploration. And so now we have a really nice 50-50 mix of those kinds of experiments, where and you'll hear about some today that are mostly focused on astronaut health. You'll hear about others that are really focused on medical applications back here on Earth. Of course, the great thing is science is one body of knowledge. So as we learn more about deconditioning of the hearts in astronauts, that provides information about deconditioning of hearts in people that have been injured back here on Earth. So we really trade that information back and forth, and almost every experiment on ISS, whether intending to benefit life on Earth or not, often has a knowledge benefit that comes back home.
And for those watching at home, remember you can use the hashtag AskNASA if you have a question. Go ahead.
Hi, I'm Christine Corbett-Moran. I'm at Caltech, and I'm with NASA's social Twitter handle, Corbett. I was curious to bring things back to potential Mars missions and space exploration, whether there are social science experiments as to, for example, the psychology of living for a year or more even in space going on.
Yes, there are social science experiments, although they're couched, I would say, as part of our biomedical research program. We call that area behavioral health and performance. One example of that kind of an experiment is a study called Journals. The crew members, and this is something we've done on ISS with 6-month crews, for a number of expeditions, and that study was completed, but we woke that study back up for the 1-year crew so that those crew members can write in their journals. And then there's a method of analyzing those, looking for specific kinds of keywords that has been applied to the journals of explorers throughout history, even back to Roald Amundsen and so forth. And so those studies really help to understand maybe things that the crew member might not recognize themselves, but that can be revealed objectively in their writing. Another example of a social science type study being done is called Interactions, and that's a study where we look at the interactions between crew members and their interactions with the ground to understand the social dynamics and how those dynamics affect decisions, critical decisions being made, and how they affect communication. And those things are really important because having good communication with the ground and good decision making in a critical situation can mean the difference between a successful mission and a really bad day.
Thanks, Julia. Let's move on to our next panelist. I introduce Michael, who's going to talk about fluid shifts in space.
Hi, I'm Mike Stenger from the Cardiovascular Laboratory at the Johnson Space Center. I'll talk about the experiment called fluid shifts. I'm just one of 3 principal investigators on the study. The other 2 are Scott Dochevsky from Henry Ford Medical and Alan Hargens from University of California, San Diego. And we have a team of 25 collaborators from all over the world, including Russian collaborators. And the reason we're doing this experiment is because of the vision issues that we've been seeing in astronauts on ISS. So to date, the number is up to 3/4 of American astronauts are coming back with changes in ocular structure and vision, all of varying severity. And it's very unclear what is causing this and why some astronauts have more severe vision issues than others. And the hypothesis is that the headward fluid shift experience in spaceflight is leading to an increase in intracranial pressure. In fact, the risk is called visual impairment and intracranial pressure. But the intracranial pressure, ICP, has never been measured in spaceflight. So at this point, it's just a hypothesis. The purpose of this experiment called fluid shifts is to try to gain more information as to why these changes are occurring in astronauts' eyes. So it's a very, very large experiment, very time-consuming, using about 100 hours of in-flight crew time to collect all these data. And our goal is to measure individual astronauts' responses to the headward fluid shift experience in spaceflight, because they all vary, they're all different, and to determine if there's a relationship between a unique individual response to this headward fluid shift and subsequent changes in ocular structure, swelling of the eye, changing of the shape of the back of the eye, which is ultimately leading to changes in visual acuity. So it's the study is we have pre-flight, in-flight, and post-flight testing. On the ground, we manipulate fluid shifts by studying astronauts while they're sitting upright like we are now. We lay them flat on their back to cause some fluid shift to the head. And then we even lay them head down, 15 degrees head down tilt, to cause kind of a massive fluid shift to the head. And while we're in these different postures, we're collecting a whole host of data. We do MRI, so we're looking at cerebral spinal fluid production in the head, drainage of the CSF, changes in the ventricles in the brain, total venous volume in the brain. We can use ultrasound to track blood flow going up into the brain and draining back out via the various drainage conduits. And so when you're sitting upright, sometimes mostly the blood is actually draining out of the back of your head through the vertebral vein. And then your jugular vein, which is the main vein, is collapsed right now. When you lay down, then that drainage switches to the jugular. And the ability of an astronaut to drain their brain may somehow impact the amount of pressure that they're experiencing in the head, which may be impacting this visual syndrome. We can also use ultrasound to measure the blood flow in and around the eye, look at the shape of the eye to see if it's flattening. We can also use ultrasound to look at the optic nerve. I've got a video. If you could play that video, the optic nerve sheath tends to distend, and the nerve itself gets compressed. So here's the video of that, and the idea is that the increased pressure in the brain is causing a change in the shape of the eye, which you can detect on ultrasound. That's a bit extreme, that shape, but the back of the eye does flatten. And so it's one of the main goals is to determine why this is occurring. We can also estimate changes in intracranial pressure for the first time in spaceflight. We flew 2 new pieces of hardware. One utilizes tympanic membrane displacement, and the other one utilizes otoacoustic emissions. What this means is that we can estimate changes in ICP by using sound waves in the ear. So there's a continuous fluid column between the brain and the inner ear called the cochlear aqueduct. So if there's changes in intracranial pressure, we can see these changes by looking at the characteristics of these sound waves that we send into the ear. So for the first time, we'll be able to relate changes in intracranial pressure to the magnitude of the fluid shift to changes in visual acuity and structure to the eye. And one final interesting piece of this experiment is that we have a countermeasure in mind called lower body negative pressure, and we plan on using a Russian device called the CASIS. They use it as a post-flight countermeasure to reacclimate astronauts to Earth gravity, but in essence what it does is it sucks the blood to your lower body. So if one of the problems with this visual syndrome is a headward fluid shift, we can reverse that by sucking the blood back down to their legs and seeing how this may or may not alleviate some of these symptoms. So Scott Kelly and Mikhail Kornienko are our first 2 subjects. They've completed their pre-flight testing, obviously, and they've completed their first in-flight session. It's like I said, it's quite a bit of testing. They have 4 days of testing in the U.S. segment. And then they pack up all the hardware, this ICP hardware, the eye cameras, the ultrasound machines, and they transport them over to the Russian segment, which is where the CASIS is anchored to a wall. They unstow, and we spent 3 days collecting data in the Russian segment and packed all our equipment back up and took it back home to the U.S. side. So we plan on doing 2 more sessions in flight, a midpoint session, and then one near the end of their 1-year mission. And be happy to answer any questions at this point.
Any early results from the experiment?
Results, it's not. We've seen what you would expect to see. We see very swelling of the jugular vein in space in some crew members, and some do not have that same swelling of the jugular. So we've got some ideas. Got some predictions on which one of those crew members may develop more severe VIP than the other, and we see some reversal of these headward fluid shifts using the CASIS. The vacuum is definitely doing what we expect it to do.
Space pants.
Space pants.
All right, well, I'll take your questions. Remember to raise your hand, wait for the microphone, state your name and affiliation. Go ahead, Ken.
Ken Kramer, Universe Today and Northeast Astronomy Forum. You talked about the astronauts suffering from ocular degeneration up to 3/4 in space. What is the effect when they come back from space? Do they all recover, or have some had permanent damage? And can you, if there is permanent damage, can you imagine some way to treat that? Thanks.
So most of the astronauts do recover, and the reason this is very important is because there are a handful of astronauts who have not recovered, even after several years of being back on Earth. And the visual acuity aspect of it, you can correct with eyeglasses, but there are structural changes to the eye that have not recovered, and I do not think that there is a way to fix that.
Go ahead.
Jim Siegel with the Celebration News. I understand why you would be trying to develop devices to minimize these problems on the astronauts. But I'll ask you the same question that I asked Dr. Robinson a minute ago about, can you envision some sort of benefits to Earthbound people as a consequence of the experiments that you're doing up in the ISS?
Certainly. Well, two of these new devices that we're flying to estimate intracranial pressure are non-invasive devices. On Earth, if you had a patient that had elevated intracranial pressure, such as a hydrocephalus patient, in order to estimate that pressure, you would have to do an invasive procedure, like a spinal tap to get at the lumbar puncture, or you'd implant a pressure transducer directly in the brain, both which come with a certain amount of risk. So there are currently clinicians on Earth that are investigating some of these non-invasive tools to estimate changes in intracranial pressure on Earth. And if it's hopeful that these will prevent certain patients from having to withstand invasive procedures. These two devices, it's important to note that they don't directly measure intracranial pressure, but they can estimate changes. So they can estimate if your intracranial pressure goes up if you change posture or if you go into space, for example.
Hi, Jared Hayworth with the Mars Society and Spaceflight Insider. My question is, has your research shown any sort of correlation between visual defects that were pre-existing, say like nearsightedness, with being affected by these fluid pressure changes in orbit? Or to ask it a different way, is it still true that someone with 20/20 vision would make the best astronaut candidate?
That's an interesting question. I think the answer is that the severity of your visual deficit does not play a part into how much worse it gets. I think that some astronauts are getting better when they go into space. So I'm definitely not an ophthalmologist, but I think those that can't see near or can't see far can see farther better. I may be wrong about that, but it has to do with the focal length of the eye, and when the eye changes shape, it changes that focal length.
Okay, not seeing any more questions. Why don't we move on to our next speaker, Alessandro?
Hello everyone, I'm Alessandro Grattoni. I'm a chair and professor at Houston Methodist Research Institute and Department of Nanomedicine in Houston, Texas. Our department is fully focused on developing nanotechnologies for medical applications. I've been doing this work in collaboration with Dr. Mauro Ferrari, who was the pioneer in the application of nanotechnology for medicine. The experiment that we are launching on the International Space Station stem for a real problem that we have in the development of implantable drug delivery system for application down here on Earth. So what we do in my lab is developing implants. We can see it in the first figure. Developing implant that can be implanted subcutaneously, can deliver drug in a very controlled fashion for extended period of time, ranging from months up to years, and therefore can deliver the drugs to a patient that may need the drug chronically, so that the patient doesn't need to have multiple injections or multiple drug administration. So by doing this, we are able to improve the efficacy, removing the problem of compliance, as well as reducing potential side effects due to the different route of administration. Now, the second figure shows the nanochannel membranes that we have developed with nanochannel as small, roughly 3 times the size of the molecule or the drug molecule that we want to deliver. Reason being is because we have observed that if you use nanochannel that small, you can achieve a constant delivery of these drugs out of an implanted reservoir for extended period of time until all the drug that is contained within your implant is has been completely administered. So these allow us to do controlled drug delivery without any sort of pumping mechanism or complex system that may actually be having problems down the line during the treatment and may render your system much complex. So the major problem and limitation that we had was that in developing this system, we have used primarily empirical, so experimental analysis. We wanted to define a mathematical model of the transport of this molecule across this nanochannel so that in a way we can design better and improve drug delivery system in the future. So the major problem is at the nanoscale. The next image, please. In the nanoscale, the molecule transport into a nanochannel is really affected by electrostatic interaction between the molecule and the surface, absorption and desorption of molecule onto the surface, as well as osmotic kind of gradients and as well as physical hindrance. So what we want to try to do is we try to decouple this system by scaling our model from the nanoscale, from the molecule into nanochannel, into the microscale. So microparticle into microchannels. These allow us also a much better control of all the components of our system, both the microparticle and the nanochannel, and we can actually observe and image the system through a regular fluorescent microscope. So what we're going to do in space is actually test the diffusion of these microparticles that mimic our molecule at the nanoscale into microchannels, parallel microchannels. You can see in the next image is actually the setup that we have prepared and that will be assembled on the light microscope module on the International Space Station. So this device includes 12 different chips. We will image them automatically. The image control and the image capture will be controlled by NASA Glenn Research Center, and we will receive the image of this particle diffusing along the microchannel. We'll do the analysis of this, and from the analysis of the images collect information for a predictive mathematical model for developing better and improved drug delivery system on Earth. So our hope is really that with this investigation, we are going to shine a little bit more light into this complex mechanism of transport that otherwise cannot be done down here on Earth, and being able to utilize it for real medical application with, again, this drug delivery system, which, by the way, are getting very close to real clinical use through in collaboration with a company, Nanomedical System, which is located in Austin, Texas. So to this project, I'll be collaborating with BioServe from University of Colorado, as well as Zin Technologies in Ohio, Cleveland, as well as Polytechnic of Torino, and obviously the NASA Glenn Research Center. If you have any question, I'd be happy to answer.
If you have any questions at home, you can use the hashtag AskNASA, and in the room, please remember to raise your hand and wave the mic. Go ahead.
Jim Siegel with Celebration News and with Spaceflight Insider. This is very intriguing, this idea of implants for drug distribution inside the body. Are there any particular either drugs or conditions, as far as scientists know now, that would be appropriate for this sort of drug delivery?
Yes, absolutely. So obviously the implant would require a minimally invasive surgery, like a little surgery can be done in outpatient procedure, but still it requires to be optimal in terms of the benefit to the patients. For this, we are targeting chronic pathologies that require drug administration for patients for the rest of their life, or pathologies that anyway require administration of drugs for a extended period of time, again, months to years. The implant that we are developing allow us for transcutaneously refilling them without need of changing them after the drug has been completely exhausted. And therefore, we would really hope to see one day this technology in people for lifetime kind of application when needed. We are looking, for example, hormone replacement is one of the hormone replacement is one of the actual applications. One of the classical examples that I bring to the people that ask me this question is the people with hypothyroidism that needs to take a pill every single day for the rest of their life. With this system, you have the potential of having the thyroid hormone analog deliver into your body, and forgetting about taking this pill, which really solves a lot of the problem of compliance. An actual much more important application is, for example, a prophylaxis for HIV. So where you want, the adherence to the treatment is very, very important. So you want to have a system that can be delivering the drug for you, so that you may not run into the risk of getting infected.
Thank you.
Very welcome.
Let's do it back.
Hi, Louis Shepard, part of the NASA social group, Twitter handle Louis Shepard. A question for Dr. Robinson back on the journaling and other experiments, the 35 on this mission and others. I would imagine there's developing an increasing number of graduate students and other scientists who are working in the various fields of research and scientific exploration that you do, what's the pipeline? Do you have a backlog, a growing channel of experiments? And if so, what's the process for choosing?
Yeah, so it's a great question. We do have a backlog of experiments, primarily for those experiments that need a lot of crew time. The automated experiments, we have great capacity on SpaceX, and we'll eventually have capacity again on orbital, and so we're able to get the experiments up when we're ready for them. But experiments that take a lot of crew time do have to wait in line. We have the prioritization process is basically Congress has told us that we need to use half of our resources for NASA's exploration objectives, and the other half of the resources should be for National Lab for benefits back here on Earth. And so we make that division, and then CASIS manages the National Lab, and they prioritize based on the economic benefit back here on Earth, and that's how they use that 50% of the crew time. And then NASA, we prioritize based on basically a complex schematic that we have of all the things we have to do to be ready to leave low Earth orbit on a variety of different missions. So we use the technology prioritization, and our human research prioritization is all based on what things we need to do so that we'll go to Mars eventually.
Hi, I'm Elizabeth, and I'm from a science museum in Vancouver, and I'm with the social team. I have a question about for my kids back home about the implants. Are they going to be tested on animals? And if so, what kind of animals will they be tested on if they're going up with the ISS?
Right. So during this experiment will be focused entirely on the basic science of the transport of molecule or particle into confinement. Now we have an additional experiment that is ongoing. We are doing animal experiment, of course, on Earth for real application, preclinical testing. We are moving closer to clinical testing with real kind of applications. So we have a second experiment that will be tested in 2017, is actually in the pipeline, 2017, in rats on board of the ISS. This is in the context of osteoporosis, so bone density loss as well as muscle atrophy. Also, this experiment has been that we are working toward has been supported by CASIS.
We have a question from social media from Moonlam asking, how long does it take to grow the veggie experiment?
So the plants that are in veggie, they take really the same amount of time to grow, a little bit slower, but about the same amount of time as they do to grow on Earth. So 2 to 4 weeks, depending on the thing that we plant in veggie.
And Lewis on Twitter asks if there's any consideration for future missions beyond a 1-year mission for even longer stays on ISS.
We are definitely talking about future 1-year missions, as well as a variety of different scenarios for doing deep space mission simulations using the ISS. And one of the things that we need to do is get some of the data back from this first set of 1-year crew members, because we understand what goes on in a 6-month period pretty well. And what we need to see is if the 12-month period is what we predict, or if there's some kind of gotcha there, where something is so different in 12 months that all of a sudden we have a new risk that we didn't know about. And that's going to really influence the final decisions that are made about additional 1-year missions.
Hi, Erin Shironi here with NASA Social. Twitter handle is @ErinShironi. You mentioned, it sounded really interesting, studying how spaceflight affects genetic expression in living organisms. I'm curious about your work with things that are less static, like blood, which is constantly changing. And I'm assuming that you monitor astronauts' biomarkers while they're in space. How do you optimize those things that are constantly changing, I would assume?
Yeah, what we really see across organisms is that there are the organism really responds to the lack of that gravity vector, and that can be because convection isn't operating in the same way. Sometimes it can be because there are cells that actually sense gravity and change the way they respond. That's turning out to be true in some plant cells even, as well as animal cells. And then you have these bigger effects of things like pressure and fluid shifts that Mike was talking about. So you have all of those things happening on this organismal basis, and each one of those you can study using these gene expression markers to really understand what's going on. So what space represents is an experiment we can't do anywhere else, where we introduce a challenge and then we can see how the genes respond and how the physical things we measure respond. It's what makes ISS such a great laboratory.
My name is Thaddeus Cesare with the Utica Phoenix. My question is for the subcutaneous implant. Is there any work being done for the security of the channel being transmitted to and from the implant? Like, can that data be observed from an outside channel? Is it a secure line?
Well, there is no real way for us to look into the nanochannels, really. It is actually very complex to do it with just electron microscopy, even taking a membrane and sectioning. We are talking about nanochannels that are in size down to 2.5 nanometers. So really, really down to the limit of the technology. So we use scanning electron microscopy and transmission electron microscopy to really kind of size this nanochannel, but there's no way of looking at and actually image this molecule and their transporting through these nanochannels. That's why we are really interested in scaling up the system 3 orders of magnitude from the nano to the micro scale, because at that point we can really use the microscopy the way we are going to do right now, the fluorescent microscopy, and track these microparticle diffusing along these channels, so that we're going to be able to do it live.
Hi, Casey Ayers. A question about the vision tests. You said that there is a machine on the Russian side that allows for the blood to be sucked back toward the bottom of the astronauts' bodies in order to judge what effect that might have. Can you explain how that mechanism works and what the astronauts need to go through for that particular part of the experiment?
Sure. Is it possible back there, guys, to show a picture? I think it's the third one I had that I completely forgot to talk about. But it's lower body negative pressure, so it's vacuum. So you put your feet into this suit, you seal at the waist, and you decompress the inside of the suit. So in essence, you're trapping blood in the lower body, preventing it from coming up. And you can control the vacuum. You can control how much blood you're pulling to the lower body. So if you use something like 55 millimeters of mercury of compression, that would simulate a fluid shift to the feet, similar to what you experience just standing up on Earth. There's a picture of it in our laboratory right there. The one on station is blue, and it's about 30 years newer than that one. We're using a lower level LBMP. We're using about 25 millimeters of mercury, because we're going to be doing it for a long time, for about an hour, in order to collect all these data. If you were to go with a higher vacuum level for a large amount of time, you would trap so much blood in the lower body that you would eventually pass out. So the Russians use this to stimulate the cardiovascular system and the musculoskeletal system about 2 to 3 weeks prior to reentry to get them used to Earth gravity again. We're using it a little bit differently.
Okay, any more questions in the room? Okay, we're going to shift over to our next panelists. They're going to talk about a new technology launching a space station that could have some really interesting implications for astronauts aboard the International Space Station. And we're back. Joining our chief scientist at the National Space Station is Dr. Jeff Norris. He is the Sidekick project lead from NASA's Jet Propulsion Laboratory in Pasadena, California. And Alex Kipman, who is the Microsoft Technical Fellow. Jeff?
Hi, and it's really a pleasure to be here today. My name is Jeff Norris, and I'm the Mission Operations Innovation Lead at the NASA Jet Propulsion Laboratory and the lead of Project Sidekick. For our social media guests, my Twitter handle is Dr. Jeff Norris. Project Sidekick its goal is to empower astronauts on the ISS with assistance when and where they need it. And we want to do that by connecting them with remote expertise and with providing something like a holographic instruction manual for certain tasks on board the ISS. When you think about the crew on board station, they have a great deal of work that they need to get done. Some of that work is associated with the operation of the space station, and some of it is associated with the exciting science that's going on board the space station, like the experiments you've been hearing about today. And we're hoping that with Project Sidekick, we can find ways to accelerate and improve the efficiency of the work that they're doing in both of those categories. And in order to do that, we formed a partnership with the Microsoft Corporation using the Microsoft HoloLens device and technologies like Skype. As you saw in that video, we've been hard at work for some time developing the Project Sidekick system and testing it. The video there was us testing it in microgravity with the help of NASA's Reduced Gravity Office on board the Weightless Wonder C9 jet. And we're also going to be testing Sidekick in NASA's Extreme Environment Mission Operations Experiments, which is an undersea laboratory, an analog for the space station, this July. And there we're hoping to learn some things about how Sidekick works in realistic operational scenarios and use what we learned there to guide some of our tests on board the space station. And I'm really happy to be joined here with my collaborator, Alex Kipman, who's brought with him an example of the device that we're launching to the space station this weekend.
Thank you, Jeff. Good morning, everyone. I'm really excited to be here today to share in this moment with you guys. This is a Microsoft HoloLens. NASA was the first ever external partner for Microsoft that we partnered with to do anything on the HoloLens. HoloLens is the first ever holographic computer, fully untethered holographic computer. And what it allows you to do is essentially create objects, but objects that instead of being made out of matter are made out of light. These things we call holograms. Now we can place these holograms right into your world, right into your life with more reality than ever before. Now this mixed reality of having holograms existing, being pinned in the real world, really allow you to create brand new experiences. Now experiences that you haven't been able to create before on any other device or any other platform. And we're incredibly excited to have Sidekick be one of those first of a kind experiences.
Thanks. Julie, do you want to talk a little bit about how these type of technologies can benefit the folks on the International Space Station?
Yeah, so, in this case, we have two purposes. One is to improve our operations efficiency, improve the way that we work, and develop ways to do more complex operational tasks. That benefits us in space. But of course, another goal of the space station is commercial partnerships so that we can use the extreme environment of space, the things that we do for life and death operations, to help benefit and change the way that we implement technologies on Earth. And so there's a great feedback back and forth between a number of the technologies that we're testing on ISS and those technologies being used back here on the ground. It's true of Robonaut, our humanoid robot on ISS in partnership with GM, and it's definitely true of the Sidekick collaboration with Microsoft.
Jeff, can you talk about that video we saw, that transition video? What were they doing there just exactly in that environment?
Sure. So the tests that we performed on the Weightless Wonder C9 jet were to study the ways that Sidekick and the HoloLens device function in the microgravity environment that we will experience on the space station. So we needed to make sure that the device, its sensors, and the software that we've written for it all performed as we would expect them to perform on board. And the tests went extremely well, and we're very positive about the expected performance of the device on board.
Great. We'll now take questions from the audience. Right in the front row.
Jim Siegel, I'm with Celebration News and with Spaceflight Insider. This is very intriguing. Do I understand correctly that that piece of headgear is kind of a virtual reality in which you would put the astronauts in various situations and let them interact with something? I'm not even sure that I understand exactly how that would work or what the purpose is. Can you give us some specific examples of scenarios where this would be used?
Absolutely. So this is a mixed reality device. It's very different from a virtual reality device. Virtual reality device will essentially block you completely from the real world and take you into a very immersive digital experience whereby you don't see the world around you, you don't see the people around you, and you're highly immersed in a very neat digital experience. These lenses, it's hard maybe to see from over there, they're see-through. You put them on, they're like a pair of glasses. You see the world around you, you see the people around you, and you can interact with them much like you would if you weren't wearing anything. Now, what the device allows you to do is then place digital assets right into the world, right in the context of the world around you. So from an experiences perspective, you can imagine, if you're trying to dock something on the space station or go through any number of procedures, you're able to now see digital assets right over the actual objects you're trying to interact with in the context of the real world. This device is capable of understanding the environment you're in. It's also capable of understanding the people that are around you, and then is able to use that information to allow you to essentially pin these holographic assets right in the world.
If I could just expand on the operational significance of that, there are two operational modes that we plan to be using with Sidekick initially. One of them we call remote expert mode, in which we allow a ground controller to see through the eyes of the astronaut using this device, and to not only speak to the astronaut like in a video conference, but also to draw annotations directly onto the world that the astronaut sees in front of them. So you can imagine this allowing us to say, for example, to tell a crew member to please turn this switch or push this button or to move this object from one place to another. It allows us to connect someone who might be the leading expert on a particular piece of equipment or a scientific experiment with the astronaut in a way that they can not only speak to the astronaut, but also show them what they would like them to do. And in the second mode, which we call procedure mode, the astronaut, without having a remote assistant, is able to see something you might imagine as an animated hologram appearing on top of the object that they're being asked to work on. So perhaps showing them how to assemble something or how to change the configuration of something for an experiment.
Laura Witten with, and I'm here with NASA Social. You had mentioned GM and Humanoid 2. Could you expand on how this collaboration is working and what new advancements you've made with it as far as where it applies to manufacturing safety? As my understanding is what one of the main applications.
So you're asking about the Robonaut collaboration? Mm-hmm. Yeah. So in the Robonaut collaboration, of course, what NASA's interested in is how to use a humanoid robot side by side to do tasks with the astronauts without causing injury or causing problems. And then eventually we'd like to use Robonaut to do mission critical tasks that might be too dangerous for astronauts in the future. So we'd even like to take Robonaut outside the ISS. So it will be a different version of Robonaut, obviously, so that we can have humans and robots really working together in exploration. But the precision, the reliability, all of the things that you need to do to be able to use robots in space drives some technological innovations that you might not otherwise do back here on Earth, where you're willing to have things be big, you're willing to have things be slow, or do whatever you need to do. So those innovations come back to Earth, and that's the nature of the Robonaut collaboration, where there's a feedback back and forth between the innovations that NASA drives because of our technological needs, and then taking those innovations and injecting them into the uses of robotics back here on Earth.
Hi, I'm Marco Hanno for the NASA Social team, and this question is directed towards HoloLens. First of all, how many hours is expected to be used by the astronauts of HoloLens, and where primarily is HoloLens going to be used inside the International Space Station?
So we're still finalizing plans on all the places and scenarios that we expect HoloLens to be used in. We're looking at some initial tests, and that would be followed by some initial operational uses. HoloLens isn't going to be confined to a specific part of the station as a device. It will work wherever the astronauts would like to use it inside the space station. And we're looking at a variety of systems related, or you might think of them as tasks associated with operating the station, as well as scientific experiments where it might be an asset to the crew.
Hi, I'm Christine Corbett-Moran here with Caltech and NASA Social. This question is for all the panelists. First of all, I'm going to start out by saying that this device looks very cool, very futuristic, and I'm excited to see the applications of it and your research. I'm also going to ask a more antagonistic question, I guess, in that I recently had the chance to participate in a Space Apps Challenge hackathon in Pasadena, and we saw that the astronauts were often using these large paper scripts to do experiments, and you would see them kind of flapping in zero gravity. And it seems to me like a quantum leap from the paper to the HoloLens. Is there something more intermediate going on in research, maybe using a smartphone or something more down to earth, to make a pun?
Yeah. I'll say a little bit and then maybe let you as well. So astronauts typically are not using paper anymore. So when you see the videos with paper, those are often from the shuttle era and so forth. They do have a printer, but they try not to print anything they don't need. So we have we do have an upgraded system that has all the procedures integrated. It can be used in an iPad type touchscreen environment, and so the crew members can work along with themselves off of those devices. So we do have that kind of intermediate step. But we find our crew time is inefficient sometimes when crew members are having to go back and forth between any kind of reference and the task at hand. And so that's one of the things that we're really going to learn from this study. Go ahead.
Hi, Casey Ayers. Two questions. First, with HoloLens, what have you had to modify or adapt for use on orbit? Anything from the ability to do head tracking and that kind of spatial programming. And then two, have you looked at using it for EVA, or is the focus exclusively on within the station at this point in time?
So I'll take the first question, and you can take the second one. As you mentioned, this thing has a myriad of sensors that understand the world around you and is capable of, essentially do spatial mapping, understand where the human wearing it is in relation to that environment, as well as understand gestures so you can do things in a hands-free type fashion. Most of these things primarily, expect you to be on Earth where there is gravity and where you can be taking calculations in real time about differentials of person moving through environment you're trying to understand all in real time. Now, the system inside of it is a very sophisticated system. It actually runs through some special silicon we've created for it, call it the HPU, or the holographic processing unit. This computer has essentially 3 co-processors on it. It has a traditional CPU, it has a traditional GPU, and it has this brand new co-processor that does all of the sensor understanding of the world that we call our holographic processing unit. Now, the space of it that handles the understanding of the environment and being able to understand the environment from both an input and an output perspective works fairly similar to how your brain works, right? We have a ton of sensors on our bodies. All of those sensors are going into your brain, and then your brain figures out in a very sophisticated way what it should be paying attention to at any point in time and what it should not be paying attention to at any point in time. In software land or in HPU land, you call that essentially a very sophisticated Kalman filter. Now, in this Kalman filter on Earth, we essentially meter more often than not data coming in kilohertz plus from the IMU, inertial measurement unit within the device. Now, when you put this in a microgravity or zero-G environment, you should expect that signal to not be behaving correctly when gravity is no longer behaving as you would expect it to on Earth. We weren't sure how the HoloLens was going to handle microgravity or space, and we were prepared to go change it to make sure it works not only on Earth and on this planet, but also outside of it. That video and the experiments we ran were to essentially find out how good is actually our Kalman filter. Written perfectly, much like your brain, it adjusts. And it stops paying attention to the fact that there's no gravity, and it starts paying attention to the other visual cortexes of the device, and it starts making those be more heavily weighted into how it actually pins the holograms in the world. We took a ton of data. We ran I think 45 experiments in microgravity that just had to do with environmental understanding. We collected terabytes of data, brought it back to Earth, and I'm happy to say we did not have to change HoloLens to make it work in microgravity scenarios. And part of the exercise right now is to ship 2 of these up into space and run more experiments. So far, no. The brain of the HoloLens works both on this planet and outside of it, but we're always prepared to change it to make it work outside of Earth.
And just to answer your second question, all of our initial focus is focused on experiments inside the space station, but I do think these technologies of mixed reality have the potential to extend beyond that, and we'll be excited to look towards those directions in the future.
Hi, my name is Mark Johnson. I'm CEO of Descartes Labs here with NASA Social. And I think it's so cool that we can have people on the ground collaborate with people in the sky. But I can imagine this also being used for NASA teams that are just distributed on this planet to work together. Have you started to do experiments here on the ground?
So as part of the development of this project, we've done a lot of on-Earth experiments and training with crew. And I'll also add to that I think there are benefits beyond the space program of these kinds of technological developments and research. There are a lot of people on Earth who have to perform very complicated tasks in very life-critical scenarios, and medicine is one that comes to mind. And I hope that the things that we're learning through Project Sidekick are going to benefit those applications as well.
Thanks. For those at home, you can use the hashtag AskNASA if you have a question. I have one quickly for Jeff. It just made me think. I know you work at the Jet Propulsion Laboratory. Are there any implications for Mars research? I know we get footage from the Curiosity rover. Is there anything that use case there?
Thank you for that. Yes, so the collaboration that we have with Microsoft incorporates another application that we've announced, which we announced back in January, called OnSite. And with the OnSite project, our goal is to connect the scientists and engineers who are helping to operate the Curiosity Mars rover with the environment of the rover on Mars. And so through OnSite, those scientists and engineers can virtually work together on Mars alongside the rover that is performing the experiments and the exploration there. So, and really, the fact that we have these 2 efforts now underway with mixed reality within the agency, I think is also just a sign that the potential of this technology is something that we're excited about, and that there are, we expect, many applications of these mixed reality technologies to the agency's work and, and beyond.
Sawtooth, could you demonstrate the glasses, please?
These I actually am not going to here. These are my personal pair, actually. I just brought them. They're our latest and greatest, and right here on stage right now. No, thank you.
Okay, if you have a question, please raise your hand. Julie, I'm curious, the eyes, you're looking really closely at something. Is there any implication of that on space? I mean, could it be harmful to the eyes as focusing? I know that's the ocular studies are really important in the research you're doing.
Well, I think fatigue is a good question because I think all of us have found both our eyes and our wrists stressed by using our devices too much back here on Earth, and you would expect the same kinds of challenges to affect astronauts. Also, and that's one of the reasons why getting to test this in an operational environment is so important, to really see how that works and how the crew will provide a lot of feedback, both to JPL and to Microsoft, about how it felt to use it, how was it different than what they did during training, and whether or not they think this would be helpful over the longer term.
And I'll just add that as part of the certification of the device for launch to the space station, when we collaborated with the doctors and the other safety officers who are responsible for making sure that these things are safe for the crew to experiment with on orbit. And those initial tests here give us a lot of hope that they will be something that they can use on board, and then we hope to learn even more on board.
Now, just add one last bit to that, which is this is a consumer product, right? And at the end of the day, you're made to use it for several hours of the day, many days of the week, and children and adults are alike on Earth. And from that perspective, making sure that people on Earth don't fatigue wearing this device is something that took years of development at Microsoft to go make sure that people don't fatigue. when they see the holograms, and that they can see and interact with these holograms for many, many, many hours of the day without any vestibular discomfort.
Hi, I'm David Liano with NASA Social at David Liano. You've mentioned that the HoloLens is a mixed reality device. We've heard the term augmented reality. Is there a difference between both?
Yeah, yes, it's a great question. In the same way that, if you can think about virtual reality as this idea that you don't see the real world and you're being essentially taken to immersive digital environment, augmented reality is this idea of you more often than not placing a piece of digital asset in front of the user, in front of the person wearing or looking through the device, phone, tablet, or PC. The key difference of a holographic unit or mixed reality is that these things are actually pinned to the real world. They actually get grafted on a surface in the real world, and you can start walking around it. You can come in and out of the room, and the thing will still be in the same spot. So this idea that we have fundamental environment understanding and spatial mapping with spatial sound of that environment, and that the objects just sit there, the holographic objects, with that recognition, it's what separates the two. Said differently, in augmented reality, you might see just a call card with some lightweight information that kind of moves with the head of the person, whereas here, you can literally see your little Minecraft characters running on top of the table, and you can move around that table, and they'll still stay where they're supposed to. Really taking advantage of 50% of the real world, 50% of the digital assets, which is where the word mixed comes in. The real world plays just as much into the experience as the digital assets you're pouring into them.
Hi, I'm Elizabeth, and I'm from Science World in Vancouver and NASA Social at Science World CA is my handle. And my question was actually about holograms. Exactly what is this sort of going to look like if it's like jumping around on the table, that sort of thing? If it's like, what's the distance that it's going to be? Is it going to be just like on Star Wars where it's like flashing in and out, or is it like an outline? I'm trying to visualize.
That's a great question, and I would say you can go look us up on Twitter at @HoloLens. There's tons of videos out there from a lot of our experiences. To equate it to the Star Wars Princess Leia, think about that one as being interlaced blue and kind of finicky. These things are super high definition, full color, holographic objects in the real world. And yeah, I would say go watch the video. It's the clearest example of what it feels like. They're see-through, right? At the end of the day, we're adding photons to the back of your eyes, which means I don't get to do black. Black is lack of light, which makes them translucent, right? You can see through them, but they feel anchored and pinned in the real world in a very believable form. And you can have little humanoid characters running around. You can have CGI characters running around. We just came from our one of our latest conferences was E3. It's where gamers go to talk about entertainment for the next year. And we just showcased one of our key franchises, Minecraft. If you have kids, you probably know what Minecraft is. And we showcased a version of Minecraft that's holographic, where you could essentially see your entire Minecraft world on top of a table and interact with your little CGI characters of Minecraft on top of a real world table. So people could come from a PC, a tablet, or a phone and interact with you live and in color on top of a holographic table with little Minecraft characters.
That is so radical. Can you tell me, is there something specific that you're worried about not working? So, coming from someone who works with like web development in some capacity, I'm curious, is there like a thing, like a little glitch or a tick that you're nervous is going to like not make it?
The product is still under development, right? It's going to come out in the Windows 10 timeframe. So people back at home, including myself, are paid to worry. And yes, we worry about the quality of the product as we start going towards ship every day. But that's what makes us good engineers. I have no doubt that in the Windows timeframe, you're going to get an amazing product that everybody's going to love.
I have a quick question for you. So you mentioned Minecraft. I'm sure gamers are wondering, can Scott Kelly on the space station play Minecraft, and can we at home play games with him?
So I'll start to answer that, and Alex might have something to add. part of the reason why we're testing Project Sidekick on board is that we see potential in these kinds of technologies as a platform. And there are other computing platforms on the space station today, things like tablets and laptops. So we're starting with a couple of applications that I described earlier as places where we think we can see some benefit immediately, but we have ideas going beyond that, and those do include entertainment and the mental well-being of the crew while they're on board for extended stays. So while we don't have a specific plan right now for a particular application like Minecraft, it is within our plans for how this platform could benefit the crew in the future.
This beautiful product is running inside of it Windows 10. So it's the same version of Windows 10 that everybody's going to get on July 29th. It has the same universal SDK and the same universal store as every other version of Windows, from the little screens to the big screens to no screens at all, which means that all of our communication, productivity, and entertainment portfolio in that app store will also be here. Now, like any version of Windows, these things are capable of being managed by the enterprise. And then the enterprise can choose, how much or how little of the App Store they make available for the people that actually have the deployment of the devices. But I hope the astronauts do play Minecraft.
Good. Hi, this is Peter Wright. I'm here with NASA Social. My Twitter handle is Frugal. I've used virtual reality, Oculus Rift, before quite a lot, and one of the challenges with Oculus Rift is performance. If you have low performance, that can induce nausea or motion sickness and all sorts of problems. We know from other presentations today that something the astronauts experience when they first arrive in a microgravity environment is motion sickness, nausea, dizziness, and so on. Does this add further complications to that?
It does not. It's a great question, and this is the part that I tried to answer earlier today around vestibular comfort. We have spent the majority of the development cycle of this product to ensure that once you put it over someone's head, it doesn't cause any vestibular discomfort to the people wearing it. Now, at the end of the day, one of the key issues you have in virtual reality land is that you actually are removing the entire world. And once you remove the entire world, unless you get every single one of your senses to work precisely correct, you end up causing discomfort, right? At the end of the day, your body is this beautiful organism that essentially says, hey, if my sensors that are all coming to my brain start disagreeing with each other, something must be going on. First, you start yawning. Let me get some more oxygen inside my body to make sure maybe I'm not breathing enough. Then you'll start burping to try to see if there's something that needs to come out. Eventually, you throw up, which is you trying to expel any poison that you put into your body. And there's just normal mechanism. If your sensors are disagreeing with each other, eventually you throw up because you're likely poisoned. Now, if you're inside a pair of VR goggles, unless you get things to be precisely correct, you will get some amount of sensors in your body disagreeing with each other, and it could cause some amount of fatigue. Now, my friends over in VR land have also spent a tremendous amount of time trying to fix all of these issues. And even if you played with some Oculus Rifts in the beginning to the latest ones that they're going to ship next year, they've made tremendous progress in those types of issues. In this guy, you essentially are seeing the real world. This is a huge, huge difference and a huge bet. You actually do get all of your sensors of the real world to play. Your eyes see the real world as it is. Your ears hear the real world as it's supposed to be. And ultimately, those things will still talk to the back of your brain, which is a big IMU or inner ear stuff that needs to agree with your ocular systems. And then we spend a ton of time, because at the end of the day, these holograms you place in the real world, the way to make you not fatigue is getting them to be correct in both space and time, right? From a space perspective, you want to make sure that as we're painting these holograms, that they're not flickering or jittering. If they start doing that, your brain is going to say that object must not be of this earth. I must be poisoned. Maybe I have to fatigue. And from a time perspective, you want to be able to paint these holograms at the same type of time slices that you can actually perceive the real world. So in one, you should think in, microfractions of milliradians of precision. Milliradians are, radio distances from the person at about a meter range. those things, we spent a ton of time to make sure that the holograms, and if you read about it and people that have experienced this, the first thing that they say is, oh my God, the thing is so solid and so much, correctly pinned in the real world. That's because we are able to place these holograms in space correctly. And then from a time perspective, you need to be able to do these things in frequencies that are, under think single-digit milliseconds. And if it takes you longer than that to be able to analyze the entire environment, calculate everything, and then reproject the object in the correct place as the human is movement, again, that can cause fatigue. HoloLens stabilizes holograms in both space and time in a way that normal humans on Earth won't fatigue, and you should expect that the astronauts tend to be significantly more well-to-do in that space.
And I'll just add, this has operational significance for us as well. We need to be able to place these annotations into the environment of the astronaut in a stable fashion so that they can be relied upon for operational instruction, telling the crew the task that we need them to accomplish or helping them through a complicated experiment. And of course, the testing of how the weightless environment interacts with all of the technologies that Alex was just describing began with our tests on board the C9 jet, and they'll continue on board. But so far we feel very positive about that.
We have a little bit more time for questions. If there's some in the room on social media, please use the hashtag AskNASA. I have one quick question here. You mentioned Skype earlier. Can Scott Kelly on Space Station, can he talk to his family and friends using the device?
That's a great question. So Scott Kelly is our first expected user of Project Sidekick on board. And it's something that actually, when we were training with Scott earlier on, something that he brought up as an area of interest for him. And it makes perfect sense to me that a person in a extended stay on board the space station would want new ways and more intimate ways to connect with the people that are here on Earth. So while we haven't scheduled a specific call time or something like that for Scott to use the device in that way, it's definitely something that's on our radar.
Awesome.
This is a question from Twitter, and it goes back to Dr. Robinson. While you're growing lettuce on veggie, what kind of vegetables are not suitable for space travel?
So that's a good question. The biggest problem we have with space travel is volume. So we want to grow things that are pretty small in volume and that grow pretty quickly as well. We also have learned a lot about how plants grow in space, and some plants are more or less sensitive to there not being gravity there, or more or less sensitive to water not behaving in the same way that it does here on Earth. So you can imagine that, you've seen pictures of astronauts playing with water bubbles. Well, that's what's happening in the soil as well. The water is distributed everywhere rather than draining down to the bottom. So that can affect the roots of some plants. So scientists look at all of those things in choosing the kinds of crops to try and grow. And then, of course, they look at the nutritional need, which is what caused us to settle down on looking at some of the greens.
Hi, Erin Sharoni here with NASA Social. It seems like a tool like HoloLens has some really interesting applications when it comes to learning, obviously not just on the space station or with astronauts, but have you looked at it in terms of learning disabilities or even things like attention deficit disorder, which are so common now? It seems like it could be fairly helpful.
That's a great question, and we do spend a ton of time in education as a vertical in terms of applications of HoloLens and Windows 10 in general. End of April, beginning of May of this year, we stood up on our main developer conference. It's called Build, and we showcased a partner on stage, which was Case Western Reserve University with the Cleveland Clinic. And now these were folks that were exploring using HoloLens as a means to teach medicine in a brand new way, right? To take it and essentially redo the Cleveland Clinic and Case Western Reserve University to teach medical and medicine in a brand new way. If you think about medicine today and the way that students learn medicine, is still primarily done on cadavers and on medical illustrations. Now, this is something that hasn't really made a ton of progress in terms of how we teach our students medicine in over a century. Because honestly, simply, there hasn't been a better way. Now, with something like HoloLens, you are able to now teach medicine in full volumetric space, where you can see the human body in its full form, and we demonstrated this on stage. And with one caveat, that cadavers, they don't move. It's really hard to understand how a human body works when you're actually alive, when you're studying something on a cadaver. Now, in a hologram, you don't have those types of issues, right? And at first, we were able to, inside a human, see how blood flows, as an example, right? And for students that had been in medical school, seeing that holographically, a lot of different things started lighting up in their brains of some things that they just could not visualize with medical illustrations or cadavers. It also gives you the ability to zoom into things, right? And we had this, and we showed this on stage as well, where medical students can zoom into the heart. The heart, at the end of the day, is a beautiful, beautiful organ, but it's not much bigger than a human fist. Now, if you want to see how blood flows inside and outside of the heart, with the heart kind of cut halfway through it, at a size where you can actually understand and see and feel where all these little veins and blood is flowing in and out, holograms give you that ability, and give you that ability in a very easy form to go do. So the applications that HoloLens has in education, we think, are deep. And with things like disabilities and things like that, we're also doing research in that area.
And if I could add, just in the context of NASA, it's, as we've mentioned, operationally significant that we can see through the eyes of an astronaut and put eyes on the task that they're performing. But I think it's also potentially exciting to, speaking personally even, to see that perspective for myself about what is the perspective of an astronaut as they're working on the many tasks that they have to complete on board the station. It's not a perspective that's been easy for us to get until now. So I think that there are educational implications of that as well.
Lewis Shepard, Washington, D.C., NASA Social, Twitter, Lewis Shepard. So for my colleagues, I was with Microsoft last year, and I had the privilege of working with Alex and his team on this. A question for Jeff and Dr. Robinson. Non-space. So what uses have you explored, or do you anticipate exploring, in industrial design and the 3D holographic design use of the Holo Studio for manipulation and industrial design?
So that's an interesting question. As I mentioned earlier, I think that with these technologies, HoloLens and the many other technologies in the broader space of mixed and virtual reality, I believe we're very early right now, which is very exciting because I think that there's so many things that we've yet to explore about how we can use these technologies. There are a lot of ideas that we're working on. One that comes to mind that I could bring up today is that if you think about some of the tasks that we're going to use Sidekick for to assist crew at the Jet Propulsion Laboratory, where I work, we assemble spacecraft in a clean room. And in that clean room environment, it's often either not convenient, or it can be expensive or time consuming for people to go into that environment because they have to be suited up, they have to go through an airlock and a number of other procedures before they can be close to one of our sensitive pieces of spacecraft hardware. So being able to project expertise from someone who is not in that environment from a distant location into that environment, it's actually quite a compelling potential use case for us that is similar to what we're trying to do on board the station, and yet also a bit distinct. So I think that's an example, and I think there'll be many more.
We have time for one more question.
My name is Serena Shkreli. I'm with NASA Social. I was just wondering what it's going to be like if you need to have any software updates for the HoloLens, and if that's going to be able to be transmitted up to the space station. And do you think there's going to be any competition with Google Glass?
Well, that's the first one first. So we, along with the 2 HoloLens units that we're launching up as part of Project Sidekick, we've launched up a laptop which has been configured. Well, we're going to be launching a laptop that has been configured to, among other things, allow us to perform software updates and any kind of diagnosis or collection of telemetry from the devices that we need in order to evaluate this experiment. So yes, our plan is to make software updates as needed to the device and to the software that we're developing for it. With regards to your question on Google Glass, these technologies, as I've mentioned earlier, are something that the agency, NASA, is exploring in a lot of different applications. And we're, these early experiments are going to teach us about how each of these technologies is best suited for particular challenges that we have within NASA. And it may turn out that certain devices are well suited for certain challenges and others for other challenges. So I think that it's quite possible that we'll see more examples of these kinds of technologies on board the space station and in other environments that NASA is performing projects.
Really science fiction turning into science fact. I know I saw some hands out there. We'll get to you. I believe that Julie, Jeff, and Alex are going to be around for a little bit afterwards. So if you have any follow-up questions, you can ask them. Let's give a round of applause to all of our presenters today. So Sunday at 10:21 a.m. Eastern Time, SpaceX is launching its 7th cargo resupply mission to the International Space Station, launching a lot of the science that was discussed here today. You can watch on NASA television, www.nasa.gov/NASA-TV. You can also follow the mission updates at nasa.gov/SpaceX. Thanks for joining us.